Hello class, and welcome to the lighting portion of this course. In this module, we'll be going over how to understand lighting and lighting efficiencies, starting off specifically with the electromagnetic spectrum. So the goals of this particular portion of the course is to give you students the tools to be able to walk into a room and say with some confidence, some certainty, whether the lighting in that space is appropriate or not. And not just from a cultural perspective or layman's terms of, oh, it's a little bright or dim, or maybe the color seems a little bit off, but to actually physically measure the quality of light in the space as well as its intensity so that you can go through and judge for yourself on a scientific basis whether it's meeting code or is maybe too intense for the human eye. We'll also go over measuring lighting power consumption, so how much energy is being used to generate the light in that space, and whether that's appropriate for building codes or not. All of those things should be able to add up so that you can identify ways of providing better light to indoor spaces more effectively and more efficiently than what might be there originally. So we're going to start off by just defining some terms and talking just a little bit about the physics of light. So going back to your high school physics class, remember we have the electromagnetic spectrum, where we've got a range of electromagnetic radiation, and it's emitted in different bands, and we classify those bands a little bit differently. And in between, say 700 nanometers to 400 nanometers of wavelength is electromagnetic radiation that we can actually see, and that's the visible light spectrum. So the longer the wavelengths, the more red it is. The shorter the wavelengths, the more it goes towards that blue or violet. We get a lot of that from the sun, right? That's great. We're happy to have that in the sky. And if you look at the intensity of what the sun is actually generating in terms of electromagnetic radiation, a large portion of that is in the visible band. And then we also get some infrared radiation as well. This curve is kind of smoothed out in reality. The bands are a little bit more distinct. So if we look at increasing flux, increasing intensity of the energy that we're getting from the sun, about 43% of the energy that we're getting from the sun is in this visible band. Everything else is kind of outside of the visible range, but we're still getting a lot of it, especially in that infrared spectrum. So what does that mean for lighting fixtures, right? Sun is great, but we can't always bring it indoors, and we also need to study and do things at night. And we don't want to burn our eyes out, right, by just replicating the sun inside, but we still want to provide some of the same colors. So you can get the same colors, say 2 colors of red, at the same wavelength, right? Wavelength or frequency is what's going to determine the color, whereas the intensity, the brightness, is going to be determined by the amplitude of those waves, right? And that's where that intensity comes from, that flux. And so we could have a very dim red light and a very bright red light, and the brighter one is going to have waves at the same frequency, but at a higher intensity or higher amplitude. So for artificial lighting, we're going to start off today by looking at just wavelength, particularly for incandescent bulbs. So the idea of an incandescent bulb, a classic Edison bulb, is you are running an electric current through a metal wire and heating it up so much that it actually incandesces or glows. So incandescence is the proper term for energy release through radiation. So if we think about just heating up a bar of metal at one end, at this back end, you say this is like almost like a cast iron pot or something like that. If that's on the stove, it might not be glowing, but it can still be hot to the touch. So if you were to hover your hand over this dark portion, you would still feel that heat, right? That heat is still being released. It's being released through a radiant heat exchange. Um, as the metal heats up even more, though, it's still emitting energy, but some of that energy is being emitted in now the visible spectrum. And the hotter it is, the color can actually change, and it'll go more towards that yellow or that white. So looking at just some associated temperatures above, say, 550 degrees Celsius, metal is going to start to glow that dull red, right, embers in the fire. As it gets hotter and hotter, it's going to go almost towards that white. And that relationship is described over here, where the wavelength is proportional to the temperature of the object. And that is called Wien's displacement law. He was the first to describe this, where lambda is our wavelength in micrometers, and that's equal to this constant over the temperature in Kelvin. And Kelvin is important. That's kind of how we measure the temperature of a light. So once again, just looking at the relationship between wavelength and temperature, the lower the temperature, the longer the wavelength. And if the wavelength is above, say, 800 nanometers, 0.8 micrometers, it's going to be outside the visible range. We won't be able to see it. Once again, if the temperature is a little bit higher, say, in the 1000 Kelvin range, then we're going to start getting into this visible spectrum. And if it goes much higher, if the wavelengths are much shorter, it will actually go beyond the visible spectrum. So for an artificial incandescent light bulb, we want to try and heat it up to get this electromagnetic radiation emission in the visible range. Right? And that doesn't necessarily mean that all of that energy is being emitted in the visible range, but we want to get some of that in there. So remember when we looked at the portion of the sun's energy that's being emitted in the visible range, about 43% of it is being emitted in the visible range, but we're also getting energy emitted out outside of the visible range on either end of that as well. With, say, a very hot object, when we're heating it up, we get some of that energy out in this visible spectrum, but a lot of it might still be in that infrared range. So we're putting in a lot of energy, but we're only getting a little bit of that energy being emitted as visible light, and the rest of that might be heat or infrared radiation. All right, so what does that mean when you go to Home Depot and you are shopping for a light bulb? Well, Wien's displacement law provides the means to basically identify the peak of what most of the wavelengths are going to be, and that gives us a sense of the color. So at 1800 Kelvin is kind of this candlelight color, and then this orange portion is what we would call kind of a warm white color, or a warm light. And the brighter we get, actually the hotter in terms of temperature, the more it becomes kind of that whitish, or what we call cool white color. And this is, I think, kind of best described between, say, like a cozy cafe. So on the left, we've got, say, a light bulb or a filament that is a 2000 Kelvin temperature. So that's how we would describe this kind of very warm, cozy light. Whereas if you take that temperature up to 4000 Kelvin, we get more of that blue, that bright, that clinical sort of, that kind of just hurts my eyes thinking about it, color, which might be great for, say, a lab or an industrial process, whereas at your home or a coffee shop, you want something much more in the warmer range, which is actually at a lower temperature. So these temperatures are now printed on a lot of packages for light bulbs, so you can judge for yourself if it's going to be a warm or comfortable, like reddish light, as opposed to a cold or very high temperature, harsh, very bright white light. So actual fixtures along the spectrum, so those like old sodium orangish street lights, those would be high pressure sodium lights, would be at 2200 Kelvin. Your standard incandescent light bulb, your Edison bulb, is about 2700 Kelvin. Whereas halides and fluorescents are going to be higher up in this bright white 4200 Kelvin range. All right, so just a brief review on this first portion. Quick reminder on what the electromagnetic spectrum is, and then we went over wavelength and how wavelength affects the color, and that color has a relationship with temperature, which can be described through Wien's displacement law, where the wavelength is proportional to the temperature based on that constant. All right, next step, we will be moving on to brightness. Thanks.